Any questions about the format of the exam? Okay, so again, the best way to study for the exam is to go over the homework, the lecture problems that we discuss in class, and the labs. So if you understand the problems we discuss in class, the labs, and the homework, you'll be doing fine in the exam. So let's start with this first problem. Any questions about that problem in particular? That's 2.74. I think this is a conditional probability. So there's a fact that is given in this problem. Said if a student is chosen at random, this is given from this class, and is found to have earned an A, then what is the probability that he or she is a senior? So for this type of problem, the best thing to do is just go and list the information that you have from the problem. So you know that juniors are 10 out of the 50, right? And you know seniors are 30 out of the 50, and the graduates are 10 out of the 50. Now, you also know how many of them got A's from the group. So juniors, 3 of them out of the 50 got A's. Then 10 out of 50 from the seniors. And then 5 out of 10. Right? This is 5. This is 5 out of the 50. Okay, so from total, we know that from all the students, 18 out of 50 got A's. Okay, so the question again is the probability. If a student is chosen at random from this class and is found to have earned an A, what is the probability of have earned an A based on this information? So from this list we know from juniors, seniors, and graduates how many of them got A's out of the 50, right? So 3, 10, and 5. So the probability of getting an A is the summation 5, 10 plus 3 out of the 50. So 18 out of 50 got A's. Okay, so probability of an A is 18 out of 50. Okay, so if a student is chosen at random from this class and is found to have earned an A, so you know that probability, what is the probability that he or she is a senior? So the probability that we are looking at is the probability of being a senior. This is S, this is J, and this is G. Given that you know that he or she obtained an A from the class. So from definition of a conditional probability, we know that this is equal to the intersection of those two events given the probability of A. So we know the denominator is 18 over 50. The only piece of information that we need to find is the intersection of the two events. The event in which you got an A and also a senior. What is that probability? And you can find that probability from, right. So this is the intersection of those two events. It is a senior and obtaining it. So this is 10 over 50. So if you solve this, this is 10 over 18, and this is pi over 9. Yes, sir. Again, the more detail you provide, the more points it can give you if you do something wrong. Yeah. So if you show me this, I mean, you can state this is a conditional probability and give me the answer. That's fine. But if you get the number wrong, then I cannot give you partial credit. So the more information you show, the best I can understand what you did. Yes, sir.
So, what about the way
P gives, that means that is a conditional probability, right? Based on the notation for conditional probability. And the event that goes after the line is always the given probability, or the given fact, or the probability of the given fact. Okay? So if this is the event that is given, you know that always you're going to divide by the probability of that event. Okay? In the conditional probability. And I think the next problem is also related. So 2.77. Any other questions about this one? 2.70. Oh, I had the answer there. 2.77, kind of the same type of problem. Question is, I'm assuming that you already read the problems. If you want me to read them, let me know. But I'm assuming that you already worked on them and you understand what the problem is asking. So the first question is, person enrolled in psychology takes all 3 subjects. So again, what I'm going to do with the problem is to list the information that I have. So I'm gonna, this is for math. So that probability is 42 over 100. Then we have psychology. And that probability is 68 over 100. And then we have history. And that is 54 over 100. We also have some information about the intersections. So for instance, this information here, 22 study both mathematics and history. So that is an intersection of events. So you can have math intersection history, that is 22 over 100. Right? We also have 25 study both mathematics and psychology. So math intersection psychology is 25 out of 100. And we have 7 studied history, but neither mathematics nor psychology. So how can we represent such an event? This one. 7 study history, but neither mathematics nor psychology. So that again is an intersection of events. Study history, but the complement of math, and the complement of psychology, and this is 7 out of 100. And then we have 10 study all 3 subjects. So all 3 subjects is 10. So that's all the information the problem is providing. And using that information, now we want to answer the questions. So the first question is, find the probability of the following events. A person enrolled in psychology takes all 3 subjects. Which one again?
It says after 10 studied all 3 subjects.
Oh, yes. So that would be this. Thank you. And this. Okay. So the first question is, person enrolled in psychology takes all 3 subjects. So we know that the person is enrolled in psychology. So that's a given. So using the probability that the student is in psychology, is enrolled in that course, what is the probability that it takes all 3 subjects? So that can be stated as a conditional probability as follows. The probability is taking all the subjects given what? Probability that it is in psychology. So this is equal to 10 over 100 divided by 68 over 100, which is 10 over 68. Make sense? Part B, person not taking psychology is taking both history and mathematics. So now we need to find the probability that person is not taking psychology. That's the given. So this is the probability of H intersection M given that is not taking psychology. Okay, so the probability of not taking psychology is the complement of this 68, so that will be 32 over 100. And the probability that is taking history, math, but not taking we have 22, but this is saying, okay, it's taking both, so this is 22. But we need to account for the event in which you are not taking psychology. Bless you. And we don't have that event defined here. But we do know this. Right? We know who are taking this, and this. So we can subtract this amount from the ones that are taking history and math. So this is 22 minus 10. So this is 12 over 32, which is 3 over 8. So we know this. And we know this. So using that information, we can find who's taking both history and math and not taking psychology. And that's part B. Yes, sir.
How come, well, reading part A, it feels like that's for the intersection of
It says, a person enrolled in psychology takes all 3 subjects. So you know that the student is taking psychology already. What you want to know is if it's also taking the other 2 subjects. So what is given is the student is taking psychology and you want to know if it is also taking the other 2 subjects. So you need to include that event in which the student is also enrolled in psychology.
I guess it feel like if you just take psychology and then psychology,
Oh, okay. I see what you're saying. But that would be the probability that the student is involved in all 3 subjects. What we are asking here, and it's kind of similar, but it's not the same, because the question comes from the fact that you already know that the person is already in the course. So that's given. And now you want to know, okay, the person is in psychology. Given that fact, what is the probability that it is also enrolled in the other 2? Whereas if you ask the question differently, like what is the probability that the student is involved in all 3 subjects, is a different question. Okay? And it's kind of confusing, but remember, the probabilities are not stated facts. These are the chances of that event happening. Okay? So saying that it is the probability of being enrolled of all 3 subjects is 50%, that means that there is a 50% chance that that person is not enrolled in those 3 subjects. But here we're saying we know for sure that the person is enrolled in psychology. So I know, based on that fact, what is the probability that the student is also enrolled in the other 2. Okay? Okay. Any other questions? Yes. Mm-hmm. Okay, so let's look at the question one more time. So the person not taking psychology, you know that the person is not taking psychology. He's taking both history and mathematics. Okay, so the stated fact is, what we know is that the person is not enrolled in psychology. So that probably is part of the intersection of events, which is right here. And we want to find out, given that fact, if the student is taking the other 2 courses. Okay, so what we are doing is, we know the intersection of the 3 events. So these are the only students who are taking all the courses, right? So you know these 10 students are enrolled in these 3 subjects, okay? We also know the total of students who are enrolled in math and history, which is 22. Right here. Okay, so the difference between those two is going to give you from this group, those students who are taking the two subjects but are not taking psychology. Let me see if I can find another way to do it. Maybe with the Venn diagram, they make things easier.
Sure, not matter. You treat them like multiplication.
Like multiplication?
And you do like n times h.
Then I will make things a little bit more confusing. So these are the intersection of the three events. So the question is, and we know this is sample space, and let's call this math, history, and psychology. Okay, so the question is saying, let's focus on the numerator first. So the intersection of math and history is this area. Right? That's the intersection. And the intersection of math, history, and psychology will be this area. And I think from here we can see what's going on. Okay, so if we said this area is larger because it includes all this area, math and history, but when you add the fact that you have also psychology, the area will become smaller. And that's why you have less number of students. Now, if you want to find the probability that the intersection of history and math is excluding that portion that is psychology, then you're going to only focus on this portion. And that's the probability that you're trying to find. Okay? That makes sense? No? Great. So this is a portion, that's the numerator, and the stated fact will be the given probability. Got it? Every time you have this type of problem, I think it will be very easy or easy way to understand the probabilities and the difference between those probabilities by drawing a Venn diagram. Okay, that's a very important tool, and it will give you a better understanding of what you're trying to find. Okay? Any other questions? You have a question? No? Okay. Okay, so the next one is also a conditional probability, the probability that the married man watches certain television show. It's 0.4, so I'm going to put that probability here as probability of husband. Yes. This one? This is the same. Yeah. Yeah. Okay. So the probability of a husband is 0.4. Probability of wife watching that show is 0.5. And the probability that the husband will watch the show given that the wife is going to watch the show is 0.7. Okay, so I think I have that here. So again, these are the names of the events. Husband watches a certain show, wife watches the same show, and this is a probability given that his wife does. Okay? So the first question is, a wife watches the show given that her husband does. I'm sorry, the first one is a married couple watches the show. So both of them are going to watch the show. How do you find that probability? That's the intersection of the events, right? The area in which both events overlap. So it's going to be this area, right? So we can find that probability as probability of A oops, this is HW. These events are not independent, so we cannot multiply the events. So we need to find another way to find this probability. Any idea? Correct. So we can use the formula for the conditional probability to find the intersection of the events. So remember, P given just is this equals P A intersection B P of B. So we can solve for this, and this is going to be P A intersection B will equal P of B times the probability of A given B. So for that problem, this will be P of W times P H intersection given W. And this is a multiplication. So we know the probability of W, this is 0.5, and we know probability of H given W, this is 0.7. So this is equal to 0.35. Okay, so the problem is basically showing you that you can use this conditional probability expression, and you can solve for the intersection, and you can also solve for the given event. Yes. So you know that the probability, actually, there's this right here. Yeah, the problem is not telling you at any point that the events are independent. And this conditional probability is giving you an idea that those events are overlapping at some point. So in most of the problems, when they are independent, it's going to state clearly that it's independent, that the events are independent. On the other side, for this conditional probability, once you find that there is a conditional probability that exists, you know that there is some overlapping between the events. Okay? The other way that you can see, I'm sorry, is if this probability equals this, then you know that the probabilities are independent because it does not affect the probability of the man watching TV. So the event that the wife watched the TV does not affect the probability that the man watches the TV. So in other words, if this was the case, that means that the events are independent because one event has no effect on the other. But that's not the case here. Okay, so you know that there's some effect of one event onto the other. That makes sense? In the scary faces. So, going back to the definition of independence, and two events are independent, that means that both events are mutually exclusive. So if you're going to represent that in the Venn diagram, that is this. They are independent, mutually exclusive. There's no overlapping between those two events. Okay, so if this event has a probability of 0.7 and this one has a probability of 0.6, that probability will not affect this probability because they're separate. They're independent, mutually exclusive. Now, if there's some overlapping, then you know that some area of this event is also shared by the other event. So the probability of one event will affect the probability of the other. Okay? Is that clear? So in this case, since the probability of the wife watching TV is different than the conditional probability, there's some effect because those probabilities are different. Again, if this were 0.7 and that one 0.7, that means that there's no effect of one of the events into the other. Okay. So let's try to work on the next one. The wife watches the show given that her husband does. So B, probability that the wife watches the show given that the husband watched the show. And we know how to find that. This is W intersection H, probability of husband. And we know this is 0.35 from part A. And the probability of the husband is 0.4. So this is 0.875. We found that first probability, this intersection here. So we are using that information and we are dividing by the probability of the man watches TV. Part C, at least one member of a married couple will watch the show. So at least one. So 1 or 2. Any idea of how to define that event? So at least one. Let's go back to the Venn diagram. This is husband and wife. So at least one means that one or the other or both. Okay? So that means that that probability will cover all that area. Because you have some probability of watching the show here and some probability of watching the show here. So the combination of the two will give you that probability. You need to account for this probability and this probability because the event can happen here and here. So they put both of them together, then you're going to find that probability. So that being said, what we are looking at that particular question is the union of the events. One or the other. So what you do, we know the additive rule. So this is the probability of W plus the probability of the husband minus the intersection of the events. So this is 0.5 plus 0.4 minus 0.35. And this is 0.55. Any questions? I think I'm going to skip the next problem unless you have specific questions. It's essentially the same concept. You need to find the probabilities that are given in the problem and try to identify what is the condition for each problem. So for the first one says the camper entering the lower cabin has Canadian license plates. So if we consider those two events, A, the vehicle is a camper, B, the vehicle has Canadian license plates, how would you define the first event or the first question? This is given. You know it has Canadian license plates, so you want to find the probability that a camper, what is the probability that camper entering the lower cabin has Canadian license plates? Camper. So it's the intersection of the event. How many of you said that it is the intersection, or is it given probability, or is it conditional probability? Okay, so let's consider the events one more time. A is the vehicle is a camper. B, the vehicle has Canadian license plates. So the first question is asking, what is the probability that a camper, so you know it's given, it is a camper, entering the cabin has Canadian license plates? Yes. Because it's given that the vehicle is a camper. So that would be the probability of B given A. Correct. About the second one, a vehicle with Canadian license plates entering is a camper. So it's the opposite, right? You know it has Canadian license plates, and you want to know what is the probability that the vehicle is a camper. Let me see. So that's the first one. This is the second one. The third one, the vehicle entering the cabin does not have Canadian plates or is not a camper. Does not have Canadian plates or is not a camper. So the first thing you need to notice is that that's not a conditional probability, right? Nothing given. You're basically trying to find out that none of them have Canadian plates or not decamper. Do we have any way to find that event?
Usually the complement of M complement or union complement minus the intersection.
You're in the right track. So this is an intersection of events. No Canadian plate, not a camper, right? So you want to find that intersection. So again, A and B. But what happened? This is null, right? So you want to find this for those events. So that makes A intersection B. That's one portion. So if we find that probability, do we find what we are looking for? The vehicle entering the large camper does not have Canadian plates, not a camper. Think about it, think about it. I mean, that doesn't mean that's correct. Just trying to see how you can come up with a solution for that one. And I think one of you mentioned it already. This is one or the other, right? Or, so we are not looking at the intersection. You're looking at the union of the events. So this is what we are looking for. Now, the question is, how can we find that number or that probability?
And then would you subtract out the intersection of those two events?
Yes and yes. So it's the complement of this equals 1 minus the probability of the intersection of A and B. And that is one of the rules that we stated in class. Okay, so if we know that probability, then we can find that number. And I can tell you that you shouldn't expect something like this in the exam, but this is a good exercise to see that you are understanding the concept. I mean, this question in particular. I'm not going to test you with something like this, right? And this is not telling me that you know the concept. This is basically taking you 20 minutes of the exam, right? Okay, any questions? Okay. So now we can move, I think we have a circuit system here. Any problems with that in particular? Okay. So a circuit system is given in the figure. Assume that the component fail independently, so these components are independent. What is the probability that the entire system works? So the entire system works means that all the components are working. Okay? Is that clear? So all the components are working. So we can simplify this circuit so the probability of both of these two components are working is the multiplication of those probabilities. So this is 0.49 and Same thing here. Probability of all of them are working is the multiplication of the events. So this is 0.512. Okay. So the probability that these are the probabilities that they work. So, for example, now I'm confused. So this 0.7 should be the probability that the components are working, not failing. Okay. So we have now that circuit, same circuit is simplified. So if we want to find the probability that this portion will not work, is the complement, right? It's 1 minus 512. This is 0.488, and this portion will not work is 1 minus 0.49, so this is 0.51. So how do you find the probability that the entire system will work? Again, the components are independent, so you do the same thing that you did for the components that were in series. Components are independent, so you can multiply 0.49 times 0.512, and that will give you 0.248. 248. There's something wrong here. The reason I'm confused is because I don't know if that probability is not stating that the probability is working or not working. And assuming that that is the probability that the circuit will work, or each component will work, and the question is not very clear. I don't know if it is asking about the system working or, yeah, I think the question is the entire system will work. So there's two ways in which this system can work. One way is by having these components working, all of them, and the other way is by having these components working. And so you have two options for two cases, and you need to consider both cases. So we can start with the top one. So the probability that it will work is probability that the top part work is 0.49. So the complement of that probability is 0.51. The probability that the bottom will work is 0.512. So the complement of that is 0.488. Okay, so now we can solve for the probability that the entire system will work. So in that case, what we can do is find the complement for both probabilities. So we have 0.49, the probability that it will not work, and 0.48, the probability that it will not work. So this probability will be equal, so entire system work will be equal to 1 minus the multiplication of the probabilities of the system not working, which is 0.752. So the probability won't work is 0.51 from the top. Probability won't work from the bottom is 0.48. So if we look at the intersection of both events, it's a multiplication of those two events. That will give you the total probability or the probability that the system will not work. And if you look at the complement of that, that should be 0.752. Let's look at part B. Given that the system works, what is the probability that the component A is not working? So system is working. We know that probability already. So that means that we are looking at the conditional probability of having A not working, C working, D working, E working, and given that the whole system works. So again, these are independent events or independent probabilities. So the intersection of those events, when they are independent, is the multiplication of the events. So for A, we need to look at the complement. So this is 0.3. C is 0.8. Missing one of the letters. Yeah, but the thing is, if we know that A is not working, we know that that portion will not work. So we don't have to account for B. So this will be C. Yes, but the question is for the entire system. So I guess we can see it from both perspectives. So we know that the entire system will work. So when we mention that the system will work, that means that this area will work or this area will work. That will make the system work. One of the two, or both, right? So given that fact that we know that the system is going to work, then what is the probability that the component A is not working? Okay, so if you know component A is not working, basically you're saying that the system will work through these three components, right? So we need to look at the intersection of these three events because having this component working would not make the system work. So C, D is 0.8 and 0.8 gives 0.752. This is 0.245. Okay, so I can tell you that go review these problems. You should expect something similar, something the circuit will be exact. Okay, it's not going to be like this one, it's going to be a combination of what we have done. So, just giving you a heads up try to understand the circuit that we have covered in class, because that will be part of the exam. Okay? So now we can move to other topics. This is more simple questions. Right here, this is to classify the following random variables as discrete or continuous. So I think that's pretty easy. So I'm not going to go over that unless you have a specific question about that problem. 3.2 is to basically define a random variable based on the sample space and give that a numerical representation. So again, you can list the sample space, and based on the random variable, you can, in this case, is the number of bees, is the numerical value from each alpha. Any questions about that one? And we cover several examples in class about that particular type of problem. Then we have continuous probability distribution. So let's go over this problem. Total number of hours measured in units of 100 hours that a family runs a vacuum cleaner over a period of 1 year is a continuous random variable x that has this density function. And the problem is asking to find the probability of over a period of 1 year a family runs their vacuum cleaner less than 120 hours. So this is a continuous probability distribution. So if you want to find a probability, okay, my first question will be, what type of distribution is this one? We know it is continuous. It is a density function or a cumulative distribution. It's a density function. You know that because of the notation, right? If it is capital letter, you know that it's the cumulative. So density, small letter here. That means that if you want to find the probability based on this PDF, you need to integrate. Okay? So the question is the probability less than 120 hours. And the problem is also saying that this is in units of 100 hours, which means that 120 hours will mean 1.2. Okay? Because this is stated in terms of 100 hours. If you solve the problem without taking that into account, you're pretty sure that you're going to obtain a probability that is greater than 1. So 100 and something. Or at that point, you know the probability is wrong. Okay? So you should be doing something wrong. So going back to this, we're going to take the limits. So this is the probability of x being less than 1.2. Okay, so based on that PDF, if it is less than 1.2, it will go from 0 to 1.2. But what happens? We have a function that is defined from 0 to 1, which f of x equals x. And then we have another function, f of x equals 2 minus x from 1 to 2. So if that means that this graph starts in 0 up to 1 is f of x equals x, and then I don't know how that one will look, but something, I don't know, something funny, I don't remember. So, but the shape is going to change. That's what you need to know. After 1, because the function is different. So from 0 to 1 is linear, but at this point there's a change in the shape of the function, so you know at that point the shape is going to be different. So your integration needs to take into account those changes. So what that means is that if you want to find the probability of x being less than 1.2, you need to integrate x from 0 to 1 and then add the portion that go from 1 to 1.2 for 2 minus x dx. Okay, so for the first portion from 0 to 1, you take the integration of the first part. And for the second portion, you need to integrate the second function. So if you solve this integration, this should give you 0.68.
So you're saying if it messes up on our integrations, we just have like that, we should be full credit?
That should be full credit. Okay? So this is the important part. You need to express your integration. For some reason you get this wrong, and I take points from this, not from this. Any other question? Okay, so part B is between 50 and 100. So for that portion, we know that we are looking at this range. We don't have to consider the other portion. So we have B is the probability of being within 0.5 x less than 1. So this is from 0.5 to 1 x dx. And this is 0.375. So how do you find a probability for a discrete random variable? Instead of integration, you just add, right? You add the probability of each outcome. So if I'm asking the probability from 0 to 5, then you're going to add the probability of 0, 1, 2, 3, 4, and 5. For the continuous random variable, remember, you need to use the integration. Okay, because we are looking at the area under the curve. So for continuous random variable, we are looking at this area. So that's why you need integration. Okay, any questions? Second, proportion of people who respond to a certain mail order solicitation is a continuous random variable x that has this density function. And the question is asking to show that the probability from 0 to 1 equals 1. So for that, you just integrate. For this case, we only have one function, which makes things easier. It's defined from 0 to 1. So if you integrate for those limits, you'll find that that integration gives you 1. So that's the only way to show that it equals 1. Questions? Okay, second part, find the probability that more than 1/4 but fewer than 1/2 of the people contacted will respond this type of solicitation. So again, you define your limits from 1/4 to 1/2 and solve the integration. You need to integrate the function. The limits are provided here. So this goes from 1/4 to 1/2. Those are your limits in the integration. Remember to put the function and also with respect to which variable you're integrating. In this case, we only have one variable, but if you want to use the right notation, you need to include that dx. Any questions? And this information is also posted. Solutions, everything is already online. Find a formula for the probability distribution of the random variable x representing the outcome when a single die is rolled once. So the dice has 6 faces, right? So it can land in 6 different ways, so each with the probability of 1/6. So therefore, the f of x is 1/6. That's the probability. That's your density function. A continuous random variable x that can assume values between x1 and x3 has a density function defined by 1/2. Show that the area under the curve equals 1. So for that, you need to integrate f of x between 1 and 3. And when you solve that integration, you need to show that that equals 1. Okay, so if I ask you something like this in the exam, you need to show me that equals 1. Okay, that couldn't be any other number. So has to equal 1. Part B, find the probability from 2 to 2.5. So again, you're going to integrate f of x from 2 to 2.5. That's 1/4. And the last one, what will be the limit for that part C? What are the limits for the integral? From 0 to 1.6. How many of you agree?
Maybe 1.
Yes. So remember, you need to make sure of the limits of the random variable. So the problem is telling you that the limits go from 1 to 3. Okay? So the function is defined within those 2 limits. So if you want to find the probability of being less than 1.6, your upper limit will be 1.6, but your lower limit is the lower limit for the function, which in this case is 1. So when you solve that integration, you'll go from 1 to 1.6. Yes?
On these, since since it's just a line, it's not a curve, could you just do like 1.6 minus 1 times 1/2 to your probability?
Yeah. No, because essentially what we have here is this. 0.5. So that will go from 1 to 3. But this is a line. Okay, so that probability is basically the area of that rectangle. So you can find that by just finding the area of the rectangle. That's correct. But remember, you'll go from 1 to 1.6. Okay? Any other questions? Okay. Continuous random variable x that can assume values between 2 and 5. Again, same type of problem. You have the limits of the function. The function is defined right here. Find that probability. So for the first one, you'll go from 2 to 4, right? And you solve the integration for that function. And for the second one, you go from 3 to 4. So I guess the most important thing here is for you to understand how to define those limits, because the other part is straightforward. Because the function will not change. Okay, so once you identify the PDF, most of the time it's going to be given. Once you have the PDF, you know that you need to integrate that function to get the probability, right? The difficulty is when you come to define the limits, which are going to give you that probability. So the top limit, again, is that limit is given most of the time, especially when you have a less than or equal, or a less than sign. On the other side, you can have a greater than. That will make things, you're going to have to find the limits on the opposite. So when you have this, you have px less than 2, you know that that upper limit is given, you need to find the lower limit. But when this is x greater than 2, you know that you have your lower limit and you need to find that upper limit. Okay? So in this case, those are given. Just put for part B, those limits are given. For part A, you have to use the lower limit for the function. So for 3.18, find f of x. So find f of x is find the cumulative distribution, right? So, and then evaluate 3 between 3 and 4. So f of x is the integration, and this is similar to what we did in one of the examples in class. So to find the integration, you need to define from the lower limit to the value of the function. So that value, when you're finding the cumulative, is given by the variable. So you are integrating this function. So we're switching to t here because we know that when we solve, we're going to solve for x. So it's the same integration. And once you find the expression for that cumulative function, then you have found your function, right? But now you need to define the limits for the function. In this case, actually, the limits were given here from 2 to 5. But what the problem is asking is to evaluate the probability of x being between 3 and 4. So once you have the cumulative function, in order to evaluate the probability, you just have to plug in the limits for the problem, right? You don't have to integrate anymore. You already integrated. You have the cumulative function already defined. So what you need to do is just plug in those limits into the function to find that probability. So if you were to solve this problem, you found 1/3. You'll see that when you integrate, the PDF is the same value. So you integrate the PDF, you get the probability from 3 to 4. If you already have the cumulative function, assume that you have this is your cumulative function, and you want to find the probability, then you just have to find the difference of these two probabilities by substituting the values of the limits into the function. That will give you the same probability. Okay, remember, I don't know if you took already, you take physics, the acceleration, velocity, all those concepts is basically the same idea. If you want to find the velocity, if you want to find the acceleration, you need to integrate, you need to derive. Okay? Basically the same concepts. But from the probability perspective. We have 2 more problems, I think. A couple more. Any questions about this one? This is very similar to one of the problems we discussed in class. And I can tell you right now that we're not gonna test you with something like this, including the exam. This is gonna come later in this course as the hypergeometric distribution. Okay? So we're gonna talk about this later in class one more time. So for now, you solve the problem, very good, but we're going to go over this one more time in class when we describe the hypergeometric distribution. Okay, so the next problem from a box containing 4 black balls and 2 greens, each of them find the probability distribution for the number of green balls. Okay, so again, you define your sample space, you define the value for your random variable, So the random variable is the number of green balls. So that will depend on the number of greens in your outcome for each event. And then the probability of x being equal to 1 is equal to the probability of each independent event. So here we have 4 blacks, 2 greens, and 3. Okay, so the probabilities are going to be defined based on those chances. So 2 over 6 and 4 over 6. So that's 2/3 and 1/3. So depending on each outcome, you can find the total probability. Simple, right? Any questions about this one? This part? This one? Okay.
Where's the exponent?
P of x equals x, that notation?
Yeah, and finding the individual probability. What is that?
Oh, the cube? This part? Okay, yeah, I can. Okay, so we have 4 and 2, right? So that's a total of 6. And we have 4 blacks. So that means that the probability of getting a black is 4 over 6, which equals 2 over 3. And then for the greens, we have 2 over 6, which equals 1/3. So this is the probability for drawing a black ball, and this is the probability for drawing a green ball, right? Now, we are going to take 3 balls in succession, right? And these are the possible events that can happen based on that experiment. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 2 options, and we're going to take 3 times those 2 options. That equals 8. So we have 8 outcomes. Okay? Now, we are defining our random variable as the number of green balls. So for the first one is 0, 1, 1, 1, 2, 2, 3, and 3. Okay. So now the question is, what is the probability that x equals x? So the probability that x equals 0 that's the first case, is going to be equal to the probability of landing a green ball, a black ball on the first event, which is 2/3, a black ball again, and a black ball again, which equals 2/3 cubed. That makes sense? The probability of each one of each successive ball. So if x equals 0, that means that you're going to have no green balls. So it will be the probability of drawing a black 3 times. And since those events are independent, then you multiply them. Okay? And you do the same thing for the other one. Good question. Any other question? 12, 16. The question for you is, you have those probabilities. Do you have any way to find out if those numbers are correct?
It should all equal 1.
That's correct. So once you sum each probability, the total should be 1. So that means that you're accounting for all the sample points, and that the probabilities are defined correctly. So if you add 8, 27, 4, 4, 4, 2, 2, 2, and 1, that will be 27 over 27. And remember, if I ask you to define the probability distribution for a discrete unknown variable, then you need to provide me with the table at the end. So this is a table for a probability mass function for a discrete random variable. And the numbers are coming from this same table. So we have 4 outcomes, 0, 1, 2, and 3. So the probability of 0 is 827. The probability of 1 is 4 plus 4 plus 4 is 12 over 27. When you simplify that, that becomes 4 over 9. Probability of 2 is 2 plus 2 plus 2, that's 6 over 27. Simplify 2 over 9. And the probability of 3 is 1 over 27. Any questions? Okay. What's the next problem? So the next problem is basically another continuous distribution or probability density function. So it is asking to verify that it's a valid density function. So we have 3 conditions, but if we satisfy the first 2, with the second one, we can satisfy the third one. So the first condition is that the probability sum 1. So in that case, you need to solve the equation for the limits, and that probability should be equal to 1. That's the first condition. And also you need to check that for all the values of x, the probabilities are greater or equal to 0, which is the case for that one. Part B is to determine the probability that the weight is smaller than 24 ounces. So again, less than, you will go from 24, you will go from 23.75 to 24. Those are the limits for your PDF, and then you solve for your probability. And the third one is the company decides that the weight exceeding 26 ounces be extremely rare occurrence. What is the probability that this rare occurrence does actually occur? So if you were to express that probability as an integral, what will be your limits? And that is a question. Any other one? Any other student? So for this one, if I ask you to express that as the integral, that will be the integration of 2 over 5 dx. I need to know the limits for part C. And I guess you're looking for p greater than 26. Everybody agree? Correct. And that's very important. Again, they are using the greater or 26, 26.25. Okay. That makes sense? Okay. So once you have the rest is just solving the integral. I believe this is the last one. It's one more. This is another continuous probability distribution. It is essentially the same type of problem. So I will basically ask you if you have any particular concerns about that problem. It's very similar to the previous one. So once you find the PDF, then you solve for 1. And the last one, again, a continuous distribution. The last assignment is the equipment working density function is defined for x. Calculate the probability of x being less than or equal to 1/3. So again, you'll go from 0 to 1/3 on that one. What is the probability that x exceeds 0.5? So that will be greater or equal to 0.5. So that's the first part. So again, the solution that I have is basically computing the cumulative distribution first, but you don't have to solve it this way. You can just integrate, you will get the same result. So part A will be the integration from 0 to 1/3 of 1 minus x dx, and that should give you 5/9. Then part B, what is the probability that x will exceed 0.5? So how do you define that one? Probability of x being greater than 0.5. So that is the integration from 0.5 to 1 of 1 minus x dx. And then part C, given that x is greater or equal to 0.5, what is the probability that x will be less than 0.75? So these are mixing some of the concepts that we already know. So this is the probability of x being less than 0.75 given that x is greater or equal to 0.5. And again, this is just to mix the concepts. So if you were to solve this, what would you do? Yeah, based on our understanding from the class is the intersection of the two events divided by the given probability, right? So if we change that to looking at the functions, we're thinking about the functions now. And this is a good problem for understanding the concepts. Okay, so when you look at the intersection, right, based on our definition of continuous conditional probability, we are looking at the intersection divided by the probability of one of the events, right? Now, if we look at the function then, again, I don't know how to draw that function. I'll just assume it is something like this. And the limits are from 0 to 1. And 0, this is 1, 0.5. So the intersection, right. So this is the probability that is given, but the intersection will be this portion. Does that make sense? Because we are basically looking at the area under the curve. So if we were to solve this, this is going to be the probability of 0.5 less than x less than 0.75 divided by the probability of x greater or equal to 0.5. And this is 3/4. Any questions?
You were fix one that said like validate this probability density function and it didn't equal 1. Would you give us any more questions? And, like after it, like if it was like part A, part B, part C?
I would not ask you something like that.
Like something like.
No, if I asked you to show that it's a probability density function, it would be equal to 1. Any other questions? So I guess again, go back, review the problem. I'll be checking my email during the weekend. If you send me an email, I'll try to respond as quickly as possible. And then on Monday morning, I'll be in my office. So if you still have some questions, you can stop by my office. I'll be available until the time of the exam. Okay? So do not overthink. I mean, I'm not going to prepare an exam that is going to try to trick you or try to ask you something that you have never seen. Go back, review the problem that we have discussed in class. Go back and review the homework. And that should give you a good preparation for the exam.
Would you say that the homework's harder than the test?
Say that again?
Would you say that the homework's harder than the test? Or like it's more challenging as far as the way you
That's hard to tell because there's a lot of problems in the homework. So there's some problems that are more harder than the ones that I'm going to be asking in the exam. Yeah. But not all of them. So, yeah. Okay. My experience is most of you do very well in the problems, but in the true or false questions, then is where you kind of focus a lot into the problem solving and you forgot to understand the concepts. So my experience with the students is that their goal in the mechanic type of mindset for the exam, so to start solving following a recipe. But also remember, it's important that you understand what you're doing. Okay, not always you go in the mechanic mindset and try to follow a recipe and get the solution. It's more important that you understand what you're trying to do, the concept behind that, and how can you use it. Okay. So that's why I always put some true or false questions just to make sure that you're understanding the concept. Okay. What was the question? Question?
I think that's a question on the different
It's from the homework or is second homework? If you want to leave or if you want to stay, it's up to you. You don't have to say if you need to leave. Okay. If you want to stay more time, that's fine too. Yes, go ahead. Okay. Is the automobile manufacturer that problem? Okay. Concern about the possible recall, probability of 0.25 for defect in the brake system. Okay. So this is to .56. So probability on brakes is 0.25. probability on the transmission is 0.18, and probability of fuel system equals 0.17. So that's the information we have, right? What is the probability that the defect is the brakes or the fuel system if the probability of defects in both systems simultaneously is 0.15? So we have the intersection, right? The 0.15. So point probability of brakes and fuel is 0.15, and we know and we are looking for this. Brakes right? Should make sure that I'm doing the right thing here. Okay, so we are looking for the unions of the events. We have the probability of A plus the probability of B minus, so we know this. You know that in order to find that probability, that's going to be equal to probability of brakes plus the probability of fuel minus the intersection of the two events. Now what we need to make sure is that we have all the information we need, and we do, right? We have B 0.25 plus 0.17 minus 0.15, and that's 0.27, right? So that makes sense? Part B is the probability of no defect so probability of no defect so we have these events independent. Or this is that there are no effects in either the brakes or the fuel system. So that is the complement, right, of the union of the events, which is P union B. And we have that probability already. So that should be 0.73. So the question is that there's no defect on brake or the fuel system. So we know the probability of having the union of the two. So what you do is just look at the component of that probability. That's a good question. Problem. Something that I would recommend you to do is go for these type of problems, try to solve them again without looking at the solution. Try them, then look at the solution, see how your thinking process is working. Because if you go and look at the solution, you will not learn how to develop that thinking process. So try the problem without looking at the solution, then look at the solution, then try the next one without looking at the solution, look at the solution, you will see that once you start doing that process, by the third one you will start getting most of them right. Because you're going to start looking at the similarities between the problems. Any other questions? Okay. So again, I'll be available by email and Monday morning. Let me know if you need any help. And good luck.